Hi, I'm Nikhar Arora, and
I'm Chase Hunter.
today we're going to be talking about tunneling diodes. Chase?
So, tunneling diodes, to start with a few of their applications, are used in extremely high frequency, low voltage circuits. They are very useful in these kinds of circuits because tunneling diodes can be used at incredibly low voltages and have incredibly fast switching speeds, which makes them useful for high frequency circuits. Now, in order to talk about tunneling diodes, we need to first begin our discussion with a regular diode. A diode, represented by this schematic here, is a semiconductor device with an anode and a cathode terminal. The operation of this device is fairly simple. When a positive voltage is applied across the anode and cathode terminals, current is allowed to flow through the device. The tunneling diode, shown as this schematic, is very similar. It has an anode and cathode terminal, and its operation is relatively the same. As a positive voltage is applied between the anode and cathode terminals, current flows through the device. Now, to show where these two devices differ in operation, we need to first talk about the structure of a normal diode. The structure of a normal diode is shown here. As I said, they are semiconductor devices, typically made from a silicon substrate. With this semiconductor substrate, two distinct regions are formed, a p-type region and an n-type region. These regions are formed by doping the semiconductor substrate with dopant atoms. For the p-type region, acceptor atoms, such as boron, are added to the semiconductor substrate to increase the concentration of free holes. Holes are simply a positive charge representing the absence of an electron. For the n-type region, the semiconductor substrate is doped with donor atoms, such as phosphorus. This increases the free electron concentration in the n-type region. Now, the difference in concentration between holes in the p-type region and electrons in the n-type region leads to the creation of a depletion region at the junction between the p and n regions. This depletion region forms a barrier potential that stops current from flowing through the device. In order to overcome this potential and allow current to flow through the diode, a positive voltage must be applied between the p-type and n-type regions, corresponding to the anode as the p-type and the cathode as the n-type region. When a positive voltage is applied here, the barrier potential caused by the depletion region decreases until electrons can flow from the n-type region to the p-type region, ultimately allowing current to flow through the device. Now, that's a regular diode. How is a tunneling diode different? First, in a tunneling diode, the doping concentrations used to form the p-type and n-type regions are increased by several orders of magnitude. This has the effect of decreasing the physical width of the depletion region while keeping the barrier potential relatively the same. Now, as the barrier potential here decreases, as the depletion region width decreases, this allows electrons to tunnel through from the n-type region to the p-type region, even though they do not have enough energy to overcome the barrier potential, as Nikhar here will explain further.
As these diagrams show us the energy diagrams for a normal PN diode and a tunneling diode. As Chase said, in a normal PN diode, electrons do not have the energy to pass over the barrier. Thus, the applied voltage has to surpass the built-in voltage in the depletion region so that either the barrier width is decreased and the electrons can flow easily, or one increases the energy of electrons while keeping the barrier height the same, so that electrons now have more energy than the barrier and can pass over the barrier. In a tunneling diode, this does not happen. When a small voltage is applied, electrons on the n side of the semiconductor can tunnel through to the valence spaces in the p side of the semiconductor. This tunneling of electrons is possible due to the dual nature of matter electrons possess. As we both know, electrons can behave as a particle and a wave at the same time. Thus, when widths are of the order of 1 nanometer or less, electrons are able to tunnel through them very easily. An IV characteristic here of a tunneling diode shows how the current through the diode varies with varying voltage. As one applies voltage and keeps on increasing it, the current increases rather linearly. This is the first region of the IV curve. This is called the intrinsic region of the tunneling diode, as this is the only region in which Ohm's law is applicable. As one further increases the current reaches a saturation point, as here the tunneling of electrons is maximum. As one increases the voltage, the tunneling of electrons decreases as the resistance offered by the barrier increases now. This region is really unusual of an IV curve, as when one applies more voltage, the current through the device decreases. This happens because the tunneling diode offers a negative resistance. As as now when we increase the voltage in this negative resistance region, the tunneling current will drop down to 0. And if we increase the voltage more after that, the current will start to increase. This current is due to the fact that now electrons on the n side of the semiconductor actually have more energy than the barrier and can pass over it very easily and don't need to tunnel. In this region of the ID curve, the tunneling diode displays the characteristics of a normal PN junction. These three regions make up the forward bias of the tunneling diode, as the voltage applied at the between the anode and the cathode is positive and greater than 0. When a reverse bias is applied on a tunneling diode, it behaves similar to that of a Zener diode but with 0 cutoff voltage. This is the characteristic of a tunneling diode which helps it to switch so quickly in high frequency circuits.
Diodes are semiconductor structures made up of a p-type region and an n-type region. When a positive voltage is applied between these two regions, strong enough to overcome the barrier potential caused by the depletion region, current can flow through. Tunneling diodes are a heavily doped variant of the normal diode, where at incredibly low and applied forward voltages, electrons can instead simply tunnel through the barrier potential rather than requiring enough energy to go over it. This allows tunneling diodes to be used in low voltage circuits and incredibly high frequency circuits due to their incredibly fast switching speeds. Thank you for listening.
Hell, Mr.